So in today's lesson, we're going to be predicting the likelihood of a redox reaction happening spontaneously. And when we say spontaneously, we mean that it would happen sort of on its own without the input of additional or outside sources of energy. And so before we get into that, you should have handy, hopefully, a standard reduction potential of half cells chart. And so I'm going to, from now on, use the short form redox table. And hopefully you have a laminated version to help you progress through today's lesson, because that will facilitate you identifying oxidizing agents and reducing agents very quickly. But before that, let me introduce you to how the chart actually works. So I have a truncated version here, but I'm going to switch to the longer version because it's quite long. Here it is, and it sort of extends beyond the size of my screen. So let me just identify particular aspects of it that I think will help you as we navigate through today's lesson. So first of all, I want you to notice that on the table we have the oxidizing agents on the left-hand side and the reducing agents on the right-hand side. And so when we look at the oxidizing agents, they're listed in a particular order. They're listed from the strongest oxidizing agents down to the weakest oxidizing agents. So that presumably means that my fluorine is the strongest oxidizing agent on this chart, and lithium ions are the weakest oxidizing agents listed on this chart. And now I'm going to scroll back to the top and look at my reducing agents. Now the reducing agents are listed in the opposite order, which is that they're the weakest reducing agents are listed at the top of the chart, and the strongest are listed at the bottom of the chart. So that presumably means that my solid lithium particle is the strongest reducing agent, and my fluoride ion is the weakest reducing agent listed on this chart. Now I also want you to note that all of the reactions, if we read them in the forward direction, are written as reduction halves. Okay, so remember that reduction means gaining electrons, right? Leo Ger. So the gaining of electrons is reduction. So all of these are listed in the forward direction as reductions. And that should make sense because our reduction half includes our oxidizing agents. Oxidizing agents, they themselves are reduced, which means they are gaining electrons. Okay, so to view a reaction as an oxidation, I need to kind of consider them in the reverse reaction. So in other words, my fluoride ion becoming fluorine loses electrons in that reverse direction. Okay, so that oxidation of my fluoride ion means that fluoride is acting as a reducing agent. We'll practice this a little bit more as we go on, and I'm going to switch back to my Jamboard so I can write a little bit down. Okay, so what I want to do is I want to focus right now on this reaction right here. And so just to kind of elaborate on what I just spoke about relating to that, writing it as an oxidation half or a reduction half. So if I know that it's acting as, if F2, for instance, is acting as the oxidizing agent, then it's going to gain its 2 electrons and become 2 fluoride ions. Good to go, right? And so that is my gaining of electrons. This is my reduction half. However, let's say the reaction that I'm concerned about is the reverse reaction, where F minus is my reducing agent. Then I'm going to write that reaction in the reverse order, of course, to show it as having lost electrons. So F2 plus 2 electrons. There we see it having lost electrons, and that's my oxidation half. Now, of course, remembering that my reduction half shows my oxidizing agent as my reactant, and my oxidation half shows my reactant as the reducing agent, because those are opposite of one another. Okay, so now let's get on to the specifics of this lesson now that you know how the chart is actually organized. which is to start with this piece. So I want to start with what is called the redox spontaneity rule. So a spontaneous redox reaction occurs, which means it's just going to happen on its own, if the strongest oxidizing agent, which I'm going to now call the SOA, is above the strongest reducing agent, or the SRA, on that table that we just talked about. Okay, so for instance, if on our chart we see that our strongest oxidizing agent is above our strongest reducing agent, okay, so positioned like that, that is spontaneous. However, when we identify our strongest reducing agent and our strongest oxidizing agent and they appear sort of like that, that is considered non-spontaneous. Okay, so let me give you an idea about what I mean. So I'm going to switch back to the last chart. And so imagine, for instance, that I identified that F2 right here was my strongest oxidizing agent, and for instance, Br minus was my strongest reducing agent. I can see very clearly that my OA is above my RA, and so that would be spontaneous because they're positioned like that. Okay. However, if instead I had my oxidizing agent was copper 2 plus and my reducing agent was Fe2 plus, then that's a situation where I have my OA below my RA like that, and that would be non-spontaneous. That clarifies a little bit for you how we're going to be using that chart. I'm going to suggest to you that you grab a highlighter. That's the easiest, or a dry erase marker that's great, because we're going to be, highlighting on our redox chart over and over and over again. So you're going to need to be able to wipe your previous highlights off and then reuse them every time we need to look at a new and unique question. So let's look at our first example, and I want to scaffold this really nicely for you so that you can manage all the components that are involved in identifying whether a reaction is spontaneous. So let's start with this example here. This example says list all the entities initially present in the following mixture and identify all possible oxidizing and reducing agents. When we say entities, that's just sort of a general word that can mean particle, molecule, ion, atom. Okay, so entity just means whatever the particular type of particle is, we're going to list whatever it is. So in this particular question, we're saying a copper penny is dropped into an acidified solution of potassium permanganate. So I want to remind you that in the back of your textbook, your chemistry textbook, you should be able to find in the appendix a list of all polyatomic ions and their associated charges. So on page 731 of your textbook, you'll find that the list that I'm talking about. And so if we scroll down, we can find permanganate as MnO4 minus in case you have a hard time remembering these. So no, let's list all the entities. So I'm telling you that this is probably the most important component in predicting the spontaneity of reactions. You need to get this right, otherwise you're not going to be able to identify what all the possible oxidizing and reducing agents are to begin with. So I'm going to do that. So I'm reading here copper penny, and so a copper penny involves solid copper, and so I'm going to list that. So I have solid copper, just Cu, and that's just solid. Now I'm dropping it into an acidified solution. So there's actually two components there. And the first is that it's acidified. So anytime I have an acidified solution, I have that particle that lends acidity to a solution, which is the hydronium, or for our purposes, we're just going to list H+. because that's how acid particles are listed on our redox chart. Now, this bit about solution, the fact that it's in solution implies that it is aqueous. And if it's aqueous, then it contains water. So I'm going to write out water. And then the last bit is this potassium permanganate. Now, potassium permanganate is an ionic compound, and so I need to list each ion separately. And so I'm going to list potassium, K+, and then that permanganate, MnO4. Oops, Mn. The left-hand side, or the right-hand side of my screen is being a little finicky, so I'm just going to erase this and just write that MnO4 a little bit more snugly here. Minus, there we go. So now that we've identified all the potential particles or entities that are involved in this reaction, our job now is going to be to locate them on our redox chart and then go ahead and highlight them out, and that will help us to identify whether they're an oxidizing agent or a reducing agent. So I'm going to look for each of these on my chart, and hopefully you will too. I want you to take a minute to pause the video to attempt this on your own using your redox table. So I have my redox table here. I'm going to switch to the highlighter mode on the Jamboard, and I'm going to try to locate all of the species. Now, it's really important for us to identify the specific species that we've seen, and it's important for you to know that sometimes a species may appear more than once on the chart and on either side of the chart as an oxidizing agent and potentially as a reducing agent. So let's look for Cu, copper, the element. So copper, the element, I'm seeing appears right here at the bottom a couple of times. Not sure if you noticed that, but it does, we do see it a couple of times. We need to highlight both situations. So I can clearly see that it is present as a reducing agent, so I'm just going to write Ra below it and identify it as a reducing agent. Now, the next thing I'm going to do is I'm going to find H+ on my chart. I cut off my chart a little bit too soon, so I'm going to refer to the larger version here, and I'm seeing that H+ appears right here. Just sort of, it's a highlighted section on the chart, just a little bit below where I cut off at copper 2+. So it is definitely on the left-hand side, which makes it an oxidizing agent. So I'm going to go ahead and indicate that, OA. Now you may be wondering, well, H+ appears in a bunch of different reactions. You can only select that particular reaction for that species if all of the other reactants are present in the mixture that, in the mixture that you're given in the question. So let me give you an example of what I mean by that. I'm seeing H+ is right here in this third reaction from the top. But I can't really list that reaction as being part of that reaction because H2O2 is not part of my reaction mixture. Okay, where's another example? No, I don't see it anywhere else that would make sense. Anyways, carrying on. Now I'm going to find my water. So water, you'll see, will appear in a few different places. So I've got water right here. And you should see water a little bit lower on the chart than this. Let me see. Yes, I'm seeing water right here as both an oxidizing agent and a reducing agent. So I'm going to list it as such. It is, it's an oxidizing agent and it's a reducing agent. So I'm going to list it as both. Okay, now let me look for K+. So I know that, K+ can only gain electrons to become potassium, right? And so it's going to be reduced, which means it's an oxidizing agent, and it's probably at the bottom. And here I see it. It's at the very bottom of my chart. And so it is most definitely an oxidizing agent, so I'm going to list it as such. And then lastly, I'm going to look for my permanganate ion. And so permanganate is at the top of the list, and we want to be careful here. I'm seeing that I have permanganate right here, and it's with some hydrogen ions. So I just need to make sure if I select that reaction that the hydrogen ions are actually part of the reaction mixture, and they are. It's acidified, so I can select that. But I also do see it somewhere else, which is a little bit down here with my water, but I never see it on the reducing agent side, and so I feel safe to say that it is an oxidizing agent. Okay. So there we've done it. We've listed all the entities and then we've identified them as possible oxidizing agents and reducing agents. That's always going to be your first step when you are trying to identify whether a redox reaction is spontaneous or not. So here are some notes that I have for you in terms of knowing how to label or what to pull out of a given question in terms of the species that are involved. I would say whenever you see aqueous or you just hear solution, I would list water. Okay, so add water to your list and label it as an OA or an RA. If it's an acidic solution, that means it contains H+, add it and label it as, appropriately. If it's a basic solution, if it's indicated to be in basic solution, then that means hydroxide is involved, and you're going to add hydroxide to your list of entities and label it based on whether it's an oxidizing agent or reducing agent. Now, as we saw with water, and water is not the only species that does this, but some substances can be both oxidizing agents and reducing agents. So it's really important for you to label them as both, and you'll see why as we move on. Okay, so those are some pointers for you to get you started knowing how to label entities properly. All right, so let's try another reaction. Okay, now this example says predict whether the following reaction will be spontaneous or non-spontaneous. So what I would like you to do first is to first identify all the species that are involved in this reaction and then identify them as oxidizing agents or reducing agents. And once you've done that, come back to the video and we will do a check-in and then we'll carry on from there. Okay, so I want to start with you identifying all the species. So from the reaction, I can see that I have cobalt that is reacting, and I have zinc that is reacting. I don't want to list my products because those, of course, are being formed, so I'm not concerned about them. I'm only concerned about what I start with. And so another thing that I'm noticing is that my cobalt is in aqueous solution, so I'm going to add in my water as a third species. Okay, so again, I don't want to list my solid cobalt or my zinc ions because those are produced. They're not in the reaction mixture. Okay, so now that we've done that, what I want you to do is to locate each of these species on the chart and identify them as oxidizing agents or reducing agents. So pause the video, give that a try, and then come back and we'll take it up together. Okay, so I'm going to turn my highlighting piece on here. I'm going to use the blue, and I'm going to look for cobalt 2+. And so I notice that cobalt 2+ is right here. And you don't want to highlight the whole reaction. You only want to highlight the side of the reaction that you find that particular species on. I don't see any other cobalts on my other chart, and so I think I'm good to go. And I'm going to label it as an oxidizing agent. And the next thing I'm going to do is I'm going to look for my zinc, my solid zinc, and I'm seeing solid zinc right over here on the reducing agent side, and I don't see it anywhere else, and so I am feeling pretty good about labeling it as a reducing agent. Now the last piece to this puzzle is water, and so water, as we have seen, appears on both the oxidizing agent side, right here, and on the reducing agent side. And, you know, multiple times. I'm seeing it here as well, and so on and so forth. And so those are the only occasions where I have water involved in the reaction where it's kind of like on its own, and I don't see water in conjunction with cobalt ions or zinc, so in any of these half cell reactions. So I think that I found everything that I need. Okay, so now that means that I'm going to go ahead and label my water as being both an oxidizing agent and a reducing agent. So now, hopefully you did okay with this. Now we've got to add in the bit about the position of my strongest oxidizing agent and my strongest reducing agent. So you'll remember that on the sides of our chart, the stronger the oxidizing agent, the higher it will be on the list. And the opposite is true on my reducing agent side, whereas the lower that I see a species on my reducing agent side, the stronger a reducing agent it is. So I'm looking for the species that is the highest on my oxidizing agent side. And so I'm seeing that right here. That's my cobalt 2+ is the highest on my oxidizing agent side. So I'm going to go ahead and label it as my SOA, my strongest oxidizing agent. The next thing I'm going to do is I'm going to look for the species that is lowest on my reducing agent side, and I'm seeing that that is my zinc. And so zinc is the lowest, so I'm going to go ahead and label zinc as my strongest reducing agent. And now what I need to do is, you know, I can kind of erase or not consider any of the other species that are there, and I simply want to look at the positioning of my SOA versus my SRA, and I'm seeing that my SOA is above my SRA, so that means that this reaction is spontaneous. Okay, so let's write a little bit down about that. So since the SOA is above the SRA, the reaction is spontaneous. And that's it. Okay, we're going to do some more practice to solidify these ideas. Hopefully you're getting accustomed to using the chart. Let's take a look at the next practice question. So here we have a solution of potassium permanganate that is poured into an acidified iron 2 sulfate solution. And the question is, does a spontaneous reaction occur? And if it does, what is the reaction? So what I want you to focus on is the first part of this question, which is the bit about, does a spontaneous redox reaction occur? So do all the work up to get to that point, similar to what we did in the last question, and then we'll do a check-in. And after that, once we get to that point, I will help you out in trying to figure out what the overall reaction is going to be, because that's the new piece. Okay, so give this a go, pause the video, and then begin again when you are ready. Okay, so I think it's important to have some solid notes on this to break it down for you. So I have some steps here. I'm hoping that you've completed step 1 for this reaction, and then maybe a little bit beyond. So the first step is always to list all reactant entities and identify them as oxidizing agents or reducing agents. And we're not going to worry about spectator ions, so let's get to it. So in this question, I'm reading that I have some potassium permanganate. So that means that I have K+, I have some MnO4-. It says solution, so I'm going to add in water. Now it says it's poured into an acidified iron 2 sulfate solution. So that means I have some H+, I have some Fe 2 plus, and sulfate is SO4 2 minus. And again, you've got that polyatomic ion chart in the back of your textbook to reference for that. And now I'm going to simply use my chart, my redox chart, to help me identify each of these as an oxidizing agent or a reducing agent. So I've taken the liberty of going ahead and simply highlighting on my chart. So just to make sure you understand, I just had to break up the chart into two pieces to fit it on this entire diagram. So really this end part just starts up here. And so when I'm looking at this, I'm seeing that I have MnO4 as an oxidizing agent. I have, of course, my hydrogen ion and my water and my K plus as oxidizing agents. And then I have my iron as a reducing agent, as well as my sulfate and water. So I'm going to go back and just label those appropriately. Right, so K plus is an oxidizing agent, so is my MnO4. My water is both. Hydrogen is an oxidizing agent. My iron is a reducing agent. And my sulfate is also a reducing agent. Hoping you noticed that I missed one, and I did that on purpose because I wanted you to see that, you know, iron 2 plus, iron can gain electrons and become a solid iron, but it can also lose electrons and become iron 3 plus. So we actually see it on both the reactant and the product side. So be careful with those multivalent metals to be sure that you are highlighting all of them wherever they appear. So I'm going to switch back and also label my iron 2 plus as being an oxidizing agent as well. Okay, so I've listed all my reactant entities as either an oxidizing agent or a reducing agent. Done. Now I'm going to look to see where the strongest oxidizing agent is. Strongest oxidizing agent. So let me switch back. And when I look at my chart, I can see that the strongest oxidizing agent is my permanganate half cell reaction, and because it's the highest up. And so I'm simply just going to write out that half cell reaction below where I'm writing my answer to my question. So I've got, let me go, MnO4 minus plus 8H plus 5 electrons is going to go ahead and produce Mn2 plus 4H2O. There we go. Okay, now the next thing I need to do is I need to choose the strongest reducing agent and then write out its equation for its oxidation. So remember, oxidation means loss of electrons. So I'm going to be expecting my electrons to be on the product side. So over here, let me get back to it. On the lowest species on my reducing agent side happens to be this iron 2 plus over here. So my iron 2 plus reaction, I'm going to write it actually in reverse. I need to write that in reverse because I want to show it as, you know, losing those electrons. So Fe2 plus is becoming Fe3 plus an electron. Okay, so again, I want you to notice that my electrons are on opposite sides of that reaction. I've got 5 electrons here, and I've got 1 electron here for each of my half reactions. So I can see very clearly that my electrons are not balanced, and so we've learned how to navigate that, and so I'm going to simply multiply my oxidation half by 5 to get those electrons balanced. Now I'm in a position where I can cancel out the electrons on the reactant and product side, and I can simply combine those reactions together. So to give me MnO4 minus plus 8H plus 5Fe2 plus, reacting to make Mn2 plus 4H2O plus 5Fe3 plus. Now, we haven't decided if this reaction is spontaneous or not, and whether it's spontaneous or not does not dictate whether or not we can write out a reaction, just means is it going to happen on its own. So let's analyze that piece. So, you know, I'm hoping that you saw that because our oxidizing agent is way up here, and our reducing agent, our strongest reducing agent, is way down here, that puts them in a position for this reaction to happen spontaneously. So this is definitely a spontaneous reaction. Okay, so there we go. That is it. The only other thing I'm going to mention to you is that, and it doesn't occur in this case, but sometimes you'll have both half cell reactions with hydrogens and some waters. And we just want to remember to, when we're combining our equations, that we cancel out any species that we can where it applies, as we've done when we were balancing our redox reactions previously. Okay, I've got one more question for you to try, and I'm hoping you'll give it a go on your own. So let's take a look. So it reads, predicting redox reactions. In a chemical industry, could copper pipe be used to transport hydrochloric acid? So this is a practical question, right? This is how individuals who are maybe perhaps chemical engineers or working in industry would actually use knowledge of electrochemistry in practical applications. So how would we go about figuring this out? Well, we would go through the same process as we just did. So I'm going to pause the video. I'd like for you to give this question a try and then come back when you are ready. So I'm going to go ahead and identify all of the species here. Essentially what we are looking to find out is, does copper react spontaneously with hydrochloric acid? So we need to assess what's going on here. I've got copper, which is solid copper, not the ion copper. I've got hydrochloric acid, so I've got H+, but I've also got Cl-. And because it's an acid, that means it's aqueous, and I'm going to add in water. And so there I've got all of my species that are of concern. So my next step is going to be to identify each of these on my redox chart. So let's switch over to that. I'm going to get my blue highlighter on, and let's go. So my copper may appear a couple of times. I'm not sure on this chart. So I've got copper right here, and I've got copper. My eyes are failing me, people. Is 2 below. And I've got my H+ in its usual position over here. And I don't see H+ in conjunction with any of the other species, so I think I'm okay with that. Now I do see Cl- over here in a couple of different spots, so I need to consider both of those. And last but not least, I need to consider water as both a oxidizing agent and a reducing agent. Okay, so I think I've got everything highlighted there, and so I can go ahead and label each of my species as oxidizing agents and reducing agents. But you know, to streamline this, really we know that a reaction will happen spontaneously if my strongest oxidizing agent is above my strongest reducing agent. So I can kind of just go right to that and work that out from the get-go, because it's not asking me for a reaction equation. So when I look on my oxidizing agent side, I'm looking for the highest, the species that is highest up. And for me, that appears to be the H+. And then for my reducing agents, I'm looking for the one that is lowest down, and that is lowest down. It's a little bit tricky to see because I don't have, you know, this whole chart below this one, but I think you should be able to see that in this case, you know, this copper would really be up here. if I had my chart in the right spot. And so it looks like my SOA is below my SRA. I have sort of like this situation where I have my SOA down here and I have my SRA above it, and that is a situation where my reaction is going to be non-spontaneous just because of the position of that strongest oxidizing agent and reducing agent. So I'm hoping when you did this question and you analyzed the chart to see that copper was our SRA and our hydrogen ion was our SOA, and that because of the positioning of them, this is a non-spontaneous reaction. And so what does that mean? That means that yes, in fact, copper pipe can be used to transport hydrochloric acid. And so now we are done with today's lesson. And so I'm hoping that you see value in doing some practice questions. Here are some questions that I would suggest for you. I will have open office hours today as well, so make sure that you pop into my Zoom meeting to ask any questions if you need clarification or maybe just want to do some extra practice. Take care.